More question.
Yeah, go ahead.
Uh, do we have to submit anything today?
No, I'm going to be lecturing today.
Gotcha.
I think in the upcoming lectures we'll do some in-class exercises next week from that I choose from the textbook, but otherwise recursion isn't covered in the textbook, but I think it's a useful technique and it's worthwhile to learn. But we're going to go over one of the more older computer science homework problems after we check out the Fibonacci. So when we left off, we were talking about the Fibonacci operation. Now the Fibonacci sequence. The Fibonacci sequence is the sequence that says, hey, the nth Fibonacci number is the sum of the previous two, and it starts with 1, 1. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So the next number is 8 because the previous two numbers are 3 and 5, right? That's the Fibonacci sequence. Mathematically, we can define it as, f of n is equal to f of n minus 1. And that's just because I can't do subscript, why I'm doing it in that weird notation. F of n minus 2, f sub n. So each Fibonacci number is equal to the previous number if n is greater than 2. One otherwise. So those are bit, and we did that last time with this sequence over here. We define the Fibonacci sequence as in a recursive manner, where basically the function calls itself. So we have the three things we need for a base case. We have our base case, the point at which the problem becomes so easy that we don't need to think about solving it. The first two numbers are 1 and 1, right? N equals 1 is the first Fibonacci number. N equals 2 is the second Fibonacci number. We're starting with 1 here. Okay. Otherwise, we have a recursive case where the nth Fibonacci number is equal to the sum of the previous two Fibonacci numbers. And finally, the third part that we need to make recursion work is that each of our three pieces makes progress towards the base case. Right. And since we subtract each time, n is going to get smaller and smaller. And if we get it smaller enough times, it's going to get to 2 or 1. All right. So now we ran this. When we ran this, we saw, we could, whoops, I did the whole thing where I asked to create a new desktop again. That's annoying. Wow, I created a lot of new desktops accidentally. I need to learn my hotkeys better. Okay. There we go. So now, let me do one last thing I need to do, which was, there we go. Okay, and so now we run it and we get our answer. Okay, so the which is 832,040. But we saw that as we increase the number, this would take more and more time to complete. Notice right over here, we are getting a shorter and shorter run that took longer. Each time we increase this by 1, it takes twice as long to complete. Now, why is that? Because in order to calculate n minus 1, we have to calculate n minus 2. And then we get back over here, to calculate n minus 2, we're redoing all the work that we just did, which is annoying, right? So what is a way we can get around that? Now, one way we can do, there's a couple different ways. There's some techniques, but one technique I like to do when you get into this case is called memoization, which is just a fancy way of saying we should save our results as we do it if we know we're going to be reusing them. So what I'm going to do is I'm going to create a I'm going to create another argument. I'm going to create what's very common in recursive methods, which is I'm going to create a helper method. Fib table. Okay, fib of n. So to calculate the nth Fibonacci number, here's what I'm going to do. I'm going to create a hash table. I'm going to create a table called the fib table, which is I'm actually getting, well, actually, let's call it fib lookup, just because that gets the idea of what we're going to use it for a bit better. So fib lookup is equal to, well, the first Fibonacci number is 1, and the second Fibonacci number is 1, right? 1 goes to 1, 2 goes to 2. I don't need to fill it out anymore, but those are our base cases, right? Make sense? Okay, those are our base cases. We could also leave it blank. Honestly, let's just go ahead and do that. This is going to be our fib lookup table. Basically, we're going to use this for storing all of our Fibonacci numbers. And now I'm going to call fib of n and pass this into the function. Now, what I've just done here is I've done something called, I've done two things. The first thing is I've created a helper method. And I've done that by overloading our function names. I've created a function, two functions with the same name, but Python is able, and any programming language worth its salt is able to tell the difference. How does it tell the difference? It tells the difference by the fact that I have two methods named the same thing, but with different arguments. Does that make sense? And right now we can kind of test this out by just, even though we're not doing anything with fib lookup, we can just put that in, and then let's go ahead and do 10. And wait a second. Does Python allow you to do that? Does Python allow you to overload? It does not allow you to overload. Interesting. Fib missing one positional item, fib lookup. That is frustrating. Okay, here I am talking about it like I know it. Java knows how to do it. Boo. Let me just check that. Can you overload functions in Python? Problem with teaching two programming languages. No, you cannot, strictly speaking. Darn it. You can do it in Java. Boo. Okay, so you can only give one function a name and then the name disappears. Boo. So we'll just call it fib recursive to do the recursion. No problem there. All right, fib recursive. So if n is less than or equal to 2, let's do this. So what are we going to do with fib lookup now? Well, what we're going to do is that we're going to store the results. $55. So they're there. So this method calls this method. Okay, so now what is it going to do? Well, if n is less than or equal to 2, what are we going to do? We're going to return 1. Otherwise, here's what we're going to do. I'm going to create a variable over here, fib n minus 1 I'm going to create two variables, fib n minus 1, fib n minus 2. Okay. And I'm going to put these right here, fib of n minus 2. So I'm going to replace those. I know it seems like I'm doing a lot of make work for nothing, but I'm taking this slowly because I'm trying to, while I'm working on this, I'm thinking what is the best way to do this? That makes sense to our students. So here we've got this fib of n minus 1. So what we're going to do and ask is if I'm going to go ahead and I'll define these variables, and I'm just going to set them to 0 at the moment because
shouldn't it be return fib n minus 1 plus fib? Okay.
Typo. I'm going to set these to 0. And here's what I'm going to say. If n minus 1 is in fib lookup, then get it.
Know that if you just start typing a name, it'll automatically know what, you don't have to copy and paste the variables.
Yeah. This is not on the final. It's more of a benefit to learn on your own. And now we're going to give these matching else conditions. Actually, I just thought of a even better way to do it. Yes, I did just think of a better way to do it. Silly me. Okay, so if n minus 1 is not in the lookup table, if we have not calculated it yet, then let's go ahead and calculate it. Makes sense. If I haven't figured out what the nth minus 1 Fibonacci number is, I'm going to go ahead and do so. Likewise, if I haven't figured out what the second Fibonacci number is, I'm going to go and do so. Okay, and now let's go ahead and run it to make sure it still works. Yes. So what did I do here, right? I've created a table. The table is, because it's always going, because of the way pass by reference works, this is always going to be the same table as anywhere else in the problem. Anywhere else in the, so this table is shared among all the recursive calls because it's the same table being passed as an argument. So if we've calculated n minus 1, then if I've, and no need to have these here right now because, so if I've not calculated the nth minus 1 Fibonacci number, calculated. If I haven't calculated the nth minus 2 Fibonacci number, calculate it. And when we calculate it, put it into the table so that I can look it up later. Then look up the values and add them together, which I could just simply, again, simplify. Still using recursion here, but I'm just preventing myself from doubling the amount of work. And so now when I try something like fib of 40 that I was trying to do yesterday, I can get answers. I can go up to fib of 50 even and still get answers super quick. because I'm not doubling the time it takes every time I increase this, which is pretty awesome. All right. So far, so good. Any questions on this one?
So by keeping the stored values in a list, you make it so that the program runs a lot faster?
Yes, because otherwise with this, I would have to calculate the fifth Fibonacci number. I'd have to calculate the 4 and the 3rd, and to calculate the 3rd Fibonacci number, I'd have to calculate 2 and 3. So why do we have brackets? Because they're referring to the table as opposed to a function call. We do the function calls in this if statement for this one. That way so this is a pretty advanced technique called memoization, and it's advanced because you don't always need it. And this is where basically if you have recursive functions that are basically where you do 2 recursive calls and you have to keep calling and calling and recalling things and doing the same work over and over again, it makes sense to save it. You follow? So now let's go ahead and look at one problem I really like. Okay. So this is one of the more classic problems. It is a chess problem.
Is it the 8 queens problem?
It is, of course, the 8 queens problem. What other chess problem would I give you for recursion? The knight's tour, maybe, but. So the 8 queens problem. So for those of you who have unfortunately never played chess, have never played chess or haven't played chess yet, A, fix that. B, let me explain about the queen. There's a lot of different pieces in chess, but the most powerful of them is the queen, not the king. The king is just simply the piece that if you lose it, you lose the game. But the queen is the most powerful piece. The queen is powerful because she can move any number of spaces in any dimension. And if you're playing 5-dimensional chess, that means backwards in time as well as across parallel dimensions, which is pretty cool. You should check out 5-dimensional chess if you haven't, with time travel. So, but anyway, but what does that mean? The queen can move in any direction. That means the queen can move. Let's go ahead and annotate. The queen can move up and down in any amount of spaces. She can move right and left in any spaces. So she can move across a row, up and down columns, and she can also move across the diagonals in a straight line. So because she's on a lighter square, she can move on to a lighter square. Okay, so in all, queens can move in 8 directions. The 8 queens puzzle set now when a piece is able to capture another piece at risk of being captured by another piece, for instance, if an opposing piece is in the line of sight of a queen in a straight line to a queen, we say that that piece is threatened by the queen. So the 8 queens puzzle basically says, hey, can we put 8 queens on a chessboard so that none of them can threaten each other? So none of them are in a position to capture one another. Why queens are homicidal, I don't know, but apparently we need to separate these queens. And so this board you see on there is a solution to this 8 queens puzzle. Notice that no queen is in the same row or column as each other, nor does no queen occupy the same diagonal. Make sense? Okay. So how do we solve this puzzle? Okay. Well, let's go ahead and try and talk about the most straightforward way to solve the puzzle. Okay. So first, let's define a board. And then I also need to define the random function, random dot. I just need to look up the
Are
random
you
function.
typing something out?
No, I'm on a
Okay.
different screen.
Cool.
Random dot choice. K populations with replacement sample. Great. Okay. So the most straightforward way to do this is to, the most straightforward way when you can't think of something is brute force a solution to the problem. So first things we're going to do is we're going to define a chessboard. Okay, so first off, let's define what chessboard should look like in terms of, remembering it. Our board is going to be a bunch of zeros, right? Let's go ahead and say an empty square is a 0. Okay. Right now, this is just going to represent a single row. Chessboards are 8 by 8, by the way. So here we've got a bunch of zeros, and if I change and even though I'm kind of doing a cloning operations there, even if I change one of them, it shouldn't change all that. Great. Okay. So now what I can do is I need 8 rows to make a chessboard. Right? 2, 3, 4, 5, 6, 7, 8. Now I didn't want to do this. I didn't want to do this 8 times. I didn't want to multiply by 8 again because that would be copying the memory location. It would basically give me the same row in every row. I know, weird, but there we go. So let's go ahead and print out our empty chessboard. Well, that's not very useful, right? So let's go ahead and actually print it out a bit more usefully. For row in the board, right? Because each item is a row. Print the row. That's what I'm talking about. Okay, so when in doubt, brute force a solution. Okay, so what does brute force mean? And this is not recursion, this is brute force. Okay, brute force is, as it implies, unelegant. Well, to brute force something means try solutions until you get something that works. So for our 8 queens puzzle, that means that I'm going to just randomly throw 8 pieces on the board, right? And see if it works. Does that make sense? So how would I go about doing that? How would I randomly go about throwing things on a board? Well, that's what I was looking up. And what I'm going to do is, of course, I will import random. Anytime I talk about randomness, it's a good bet that I need to use import random. Okay. So the thing about brute force is that it always works eventually, because the idea here is I'm going to check every single thing. I mean, okay, so I'm doing it at random, but I could do it in a more methodical manner, but honestly, random seems a lot more fun. So the board is basically, the board is made up of spaces. Like this over here is space 1, or sorry, this is space 0, space 1, space 2, space 3, space 4, space 5, and so on and so forth. Make sense? So each of and it goes all the way up to 63. So what I can do here is I can do something along the lines of, I can basically generate 8 queens like this for equal to random dot sample. I believe that is it. That is what I looked up. Random sample Python, right? And what sample does is that it chooses a k length list of unique elements chosen from it. It is sampling without replacement. right? Because no two queens can use the same spot. So range 0 up to, but not including 64. Great. Have I broken anything yet? Let's go ahead and see. Or does it miss it? Missing a positional argument K. It's saying, hey, you told me what you wanted to pick from. How many of those did you want again? And I want 8 queens because we have 8 queens. So queens. Okay. There we go. So there we have 8 choices. Okay, 8 spaces. And then we can just put those on the board. Okay. And for queen in queens, that's equal to 4 queen in queens. Why am I writing like that? That's not at all Pythonic. Board of that queen's position. Well, it's a 2-dimensional array, so we need the row and the column. Oof. Right. This is gonna hurt. So the row, yep, row divided by 8. Yep, queen mod 8. The pause for thought was which dimension goes where, which is awful. And you're probably going, wait, let me make sure this works before I talk about this brain exploding part, okay? Because the only reason I'm comfortable doing it is I've done it a lot. And we can see right off the bat that this is going to be a bit tricky because, we've got multiple violations in our output. We're going to get, it's going to be hard to get anywhere. But how did I place a queen like that? We're not going to need to know this for the full problem. But what I did is that basically the grid is all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so basically the first square is 0, 1, 2, 3, 4, 5, 6, 7, 8, sorry, 7. And then it wraps around 8, 9, 10, 11, 12, and so on and so forth. So how in the world do I get there? Well, what I did is I translated a 1-dimensional coordinate into a 2-dimensional coordinate. Wait, what? How did I do that? And the answer is that basically this is going to be row 0 over here, right? That's row 0. Whereas, and this is row 1. And this is going to be row 2. So the way I figured that out was, well, anything that's in the 0th in row 0, right? It's going to be 8 or less. So if I divide queen by 8, the position by the square by 8, if I get 0, it goes into this row. If I get a 1, it's going to go into this row because 8 divided by 8 is 1, 9 divided by 8 is 1, 10 divided by 8 is 1, and so on and so forth until I get to 16, which is 2. Now, what about for the Y position? Well, that's the modular portion of this, queen mod 8. So the remainder after I divide by 8, well, that would be 1. Remainder is 1, 2, 3, 4, 5, 6, 7. And then over here, again, the remainder is queen. If I'm on the first column, I'm going to be either 0, 8, 16, 24, so on and so forth. I'm going to be a multiple of 8. Otherwise, if I'm in the first row, I'm going to be a multiple of 8 plus 1. Or I'm going to be, if I'm in the second column, I'm going to be multiple of 8 plus 1. If I'm in the third column, I'm going to be multiple of 8 plus 2. So that's how I figured. So that's why we mod there for the Y coordinate. I know it's a it's a lot and it will take some reviewing and getting used to, but that's a pretty tricky thing. And I wouldn't expect necessarily anybody to figure that out in a high pressure situation, although it's a bit tricky. But so if I were to go sequentially through all our possible solutions, this would work, but I'm not going sequentially, I'm going randomly. Also, but if I'm going sequentially, it's going to take forever. I have to wade through a lot of possible decisions. Specifically, there's a lot of combinations. How many combinations am I trying with this? I'm trying, well, there's 64 places to put my first queen. Then there's 63 places to put the second, 62, then 62, then 61, then 60, then 60, then 59, then 58, and to put the seventh queen, and then to put the eighth queen, there's 57 spaces. 1, 2, 3, 4, 5, 6, 7, 8. So how many possible combinations do I have to check? And I'm not even checking them. And this is, it's not a full factorial. This is just simply the first bits because we're choosing 8 spots out of 64, but that's a large number, I think. I think that's a large number. I mean, it's certainly more numbers than when I'm looking at Age of Earth or dollars that Bezos has, or Musk, or whoever's in charge in first place in the money getting game at the moment. So yeah, that's probably a big number. And that's probably going to take a lot of time to figure out. So let's not do it this way, but it is a way that could, in theory, do it. Now, and now why is it so slow? Well, because let's say I put my first queen in the first square, and then this first queen in the second square. I don't have to worry about all the other combinations that come after it. I can prune that entire kind of dead end there because, you know, as soon as there's a violation, that's kind of getting me into a dead end. Does that make sense? So I'm not going to go forward with any dead end solutions. Here, there's nothing stopping us from going forward in dead end solutions. There's no kind of check for that because I'm going to G-checking anything. And now that's where the recursion comes in. So we're going to use a process called recursive backtracking to do this. And how does this work? 1 second. I realize I am being foolish here. Aha! Here we are. Knew this would come in handy. Okay, give me a second. Look what I have here. Handmade chessboard. Yes, it is in fact the same solution for our chess puzzle for the Sudoku. The recursive backtracking is amazing because it is the exact same solution for multiple problems. Now, because I only have 2 queens, and because this problem takes a while, I'm going to use 4 pawns, these pieces here, and we're going to do this on a 4x4 chessboard, a 4 queens problem, if you will. Let me go ahead and stop sharing for a second so that I can get my camera live, and then we're going to, let's see, we're going to put these textbooks to use and start propping them up so we can get this. Now, I actually have a good video of this in my YouTube channel of this process, but let's see. Yeah, you'll just have to deal with the isometric kind of point of view here. Okay, and in frame, yes. All right. So everybody sees my my chessboard. This is going to be a 4x4 puzzle. So the way to solve this problem is, and again, I've kind of reduced this from an 8 queens method to a 4 queens method. Okay, is that I have 4 queens. Now, first off, let's be smart here. Each queen gets her own column, right? no point in, there's no point in checking anything that's not a column, right? Let me go ahead and change my view so the recording can pick it up. View the speaker. That's not, and pin. There we go. That should work much better for everybody. Yes. Okay. So every queen has their own column. So what I'm going to do is that I'm going to basically say, okay, if I'm in this column, where do I need to put the queen? So recursive backtracking works like follows. Given my position is, or the where I am in the puzzle, iterate through all the choices I have. And then I'm going to look at the first possible choice I have. So here, basically I've got one queen. Okay. Is it safe to put the queen here? Well, yes, there are no other queen. There is nowhere else to put the queen. It is there is no other queens on the board. By definition, it's safe. So let's start with the second queen. Can I put the queen here? No, I cannot, because they're on the same row. They're on the same diagonal. Can't put them here. What about here? I can put the queen there, right? Okay. What about the next position? So now we're going to move on to the next position. Okay. So what I'm going to do over here, yes, is a dead end. I can't put it here. I can't put it here. Can't put it here. Can't put it here. So this is a dead end. So the way this is going to work is that it's a recursive call, and we're going to return true or false. When we get a false back, that means whatever solution, partial solution we had was a dead end. So we need to pick up from there. So column B gets the call that's the dead end, and it says, so moving on spot 3, B3 was a dead end. So I better go to B4. Okay, that's fine. So now let's go on to here. This is invalid. That's safe. And now let's go to the fourth part. No good, no good, no good, no good. Okay. So backtrack. No good, no good. I'm out of space. This was no good. It was a dead end. This leads us to no spaces. So now I'm going to move my queen over here. So now let's try B again. No good, no good, no good. Oh, this is a safe spot. That's a safe spot. And now no good, no good. That looks like a safe spot. No? So now we call the next column, which is here, which is invalid column. And so when we go out of bounds, that is our base condition, believe it or not. Going out of bounds in this case is good. That means we won. It means we succeeded at our puzzle. So when we get here, we'll return true, which will make this guy return true to him, which says, hey, tell the person who called me that I got a solution. Hey, tell the person I called me. I'm going to tell the person who called me I got a solution. Hey, I'm going to tell the function that called me I got a solution. And then we're done. All right. Good thing I have my chessboard just lying around here. Okay. Almost as though this was my prop I used for class. We got this. It's amazing how useful some stuff you get when you're a kid can be. That was a 3rd grade Hanukkah present. One of the few Hanukkah presents I actually remember exactly what it was, So whoops, I'm sorry about that. I just smacked the microphone. Okay. Anyway, you might have gotten the impression that I've rehearsed this puzzle a number of times. The answer is yes, I have. So give me 1 second to turn this light back on. Come on. Okay. Now let's go ahead and code this up. And this is not going to be any hit or miss stuff. This is where I'm kind of in my zone. I've done this a number of times and I like doing this one. All right. So to solve, we're going to write a function called solve. It's going to be our 8 queens puzzle. Okay. And what we're going to do is that we kind of want to be lazy when we're coding. So I'm just going to write it in kind of a pseudo codish manner, and I'm going to leave stuff, one part of it for later, so we can kind of figure it out as we go along. So solve, right? I'm going to take in the board as an argument, okay? And then I'm going to say my current column, right? So here, board is the board. Column is the current column. We are trying to put a queen on. Okay. One second, we want to try something. It doesn't want to, it doesn't, is the current column we are trying to put the queen on. Ooh, nice. All right. Just FYI, on Windows, Super H or Windows key H, voice typing. So we're going to solve the board and the column. So first things first, if column is greater than or equal to 8, in other words, if 8 queens have been put down, we're done, return true. By default, though, what we're going to do is that we're going to return false. If we can't, by default, we're going to try to solve it. If we can't solve it, return false. Make sense? Okay. So what I do basically is I'm going to iterate through all the possible choices here. So for choice, and what are all the choices? The row, each row is the possible choice. So for row in range, and what are the possible ranges? 0 to up to, but not including 8. So these are the possible range of rows, right? There's row 0, 1, 2, 3, 4, 5, 6, 7, 8 total rows. So I'm going to try to put a queen down in one of those rows. So here's the key here. If is valid to put the queen in this row and column combination. Always put your rows before the column. It's just the way it's supposed to be. So if is valid row column combination, and let's go ahead and yeah, and that is just something I'm going to leave for later. Okay. So I'll go ahead and define this function and just simply say, hey, yeah, it's true. Yeah, every space is good. No worries. Make sense? So I'm saying, hey, if the space is safe, to which I'm saying, yeah, for right now, every space is great. So if the safe is good to put a queen down in, let's put a queen there. Okay. And then what I have to do is, so I've solved, remember, the way recursion works is basically, so let's just refresh. The way recursion works is if there's a base case, okay, I'm going to solve then it's done. So again, the base case is the thing that's so easy to solve. I don't have to think about it. Where do I put the queen? Where I'm out of queen, I'm done. Okay. Here though, I'm saying, okay, I have no idea how to put down 7 queens or 6 queens or however many are left. But wait a second, I can figure out where to put 1 queen. Okay. Right. Can put 1 queen in this column, and then I can figure out the rest of the board. Make sense to everybody? Right. So again, this is kind of just being lazy about the way it's like this. Rest of this is hard. I'll figure that out later. I'm going to just work on my single column here. So if I can put a single column in this row board column, sorry, if I can put a single queen in this row column combination, great, I'm going to do so. And now here's the part where I basically say, I'm going to be lazy, which is I'm going to do a recursive call. I'm going to say, hey, if solve board column plus 1 equals true. I don't have to put the equal true there, but I'm gonna just for return true. And then I'm gonna go ahead and do this. And this is the part where basically when I introduce it in my data structures class, that's kind of when people get their brain crashing. That's okay if that happens to you. And yeah, that's pretty much it. Okay, so what is this over here? I'm saying, well, my current row, I figured out a queen. So let's go ahead and solve the rest of the board starting at this column, right? We figured that out. I've put my and again, the way this is working is that I'm moving left to right across the board. I'm starting at column 0, then I'm doing column 1, then I'm going to do column 2 and column 3. And actually, if we run this now, I'm going to go ahead and do solve board and 0. Let's move this below the solve function. Then we'll see. Give me 1 second. It should have. For row in board print row. Not work. Oh, you know what it did? It went across the top. Great. So notice that we've we've put queens across the top row. We had 0s there, and now we have 1s across the top row. Now you're going, wait a second, Professor Rosen, that's not an 8 queens. That's not a solution to the 8 queens problem, right? I think Professor Rosen has forgotten how queens move. Possibly it's been a couple minutes. My memory isn't what it used to be, but what it is that I just simply choose. I look at what I'm doing is I'm looking at the first row and I'm saying, hey, is this a valid place to put a queen? And I'm always saying yes. Now, why did I do this? So I could ensure that the recursion was working. Does that make sense? This way I can ensure that the recursion is working. Okay, now let's go ahead and work on this part. So this part, we're going to be a bit clever about, because you're thinking, oh, great, queens. Queens can check in 8 directions. That means I need like 8 freaking loops or something. And the answer is, if you want to torture yourself, yes, you need 8 loops. We do not need 8 loops, though. Because let's review first. Again, let's review. There's that magic pen of mine. There it is. Right. We have a queen. Right. Say hi to the queen. Okay. So the queen moves in one of 8 directions. But first off, the way we're doing is that we're saying, let's put a queen in this column, then let's put a queen in this column, then let's put a queen in this column, right? We are kind of just enforcing, without having to check for it, that there's only going to be 1 queen per column with the way we're doing this, right? Our code says, if we're done with this column, move on to the next column, right? We're only working on 1 column at a time. And then if this column doesn't work, aha, right. That is a bit that I do need to make sure that you understand. So you share, right? And this part says, hey, so over here, we're saying, hey, right? If we got to the end, tell the person who called me that we got to the dead end. Otherwise, we were at a dead end. Sorry. If we got to the end of the puzzle, tell the person who called me we got to the end of the puzzle, not a dead end. Otherwise, we got to a dead end. If this comes back false, we don't do this, which means we got to a dead end. which means that we put a 0 here. Okay. And if we go through all our possible, and how do we know for a dead end? Well, if we go through all our possible rows and none of them are valid, we try all the possible places to put our queen, then we got to a dead end. So we'll call whoever called us and tell them return false, which means this will be false, which means they'll know to pick up their queen and to try a different row. So going back to checking, how do we know if it's valid? Sorry about that awkward jump there. So because we're working with one queen at a time, we know that we don't have to check up and down. So we're down to 6, but that's not all. Because we're starting at column 0 and going all the way to column 8 to column 7 inclusively, we're going up in our columns. That means we're placing queens from left to right, which means we don't ever have to worry about queens being to our right, right? Because if we backtrack, we're going to pick up our queen. And so there's only ever going to be queens to the left where we've already put down queens. There's never going to be queens that we have to check to the right because we're currently on the rightmost column. So we only have to check 3 directions. We have to check up and to the left, down and to the left, and to the left. So let's, again, be lazy and work on those individually. So to work on those individually, I'm going to create 3 new functions. Def is row valid, and this will just check basically, did I put my queen in a valid row? Board row column. Return is row valid, board row column. There we go. And yes, I know that's a function calling a function there, but we're actually going to call 3 and match them together then. So this is going to kind of turn it into the 8 rooks or 8 castle problem. In other words, we're going to do everything but, check our diagonals. So what do I have to do to check to make sure that there's no queens to the left? So this first dimension is the row. So when I'm if my row is valid, I'm checking to check if my row is valid. I'm making sure that there's nobody on the same row. So this is going to be held steady. And what I'm going to do is I'm going to check if there's any other columns, so anything else in the same column as me. Sorry, if there's any, yeah. Yeah, if there's any, sorry, if there's not, if anything's in the same, anything's in the same row, by seeing if there's anything with this row at a different column that has a queen in it. So the way I like to do this is there's a couple ways to do this. I could do this like this. So, and I'm going to go ahead and assume that there's not going to be an issue. And as soon as I find another queen, there's an issue. So a couple ways to do this. I can say for space in board row, assuming it can spell, which apparently I cannot do today. Really can't. Okay. Then we see that this works, which is cool. But basically it's saying, hey, grab the row and check every space in that. If there's a 1 there, that means no good. But what else but let's go ahead and we're just trying by indices, right? So for I in range. So what I want to do is I want to check the column value. I want to check the column value. So I in range, and let's start at 0 and go. And I don't want to go out of bounds. I got to check left, but I don't want to go out of bounds. So how do I not go out of bounds? Well, I don't go out of bounds by staying above 0. Okay, so what I want is, this is going to look a bit weird, column 8 minus column. Let's see. No. Going to 0. Oh, right. No, just column there. Overthinking it. I'm guilty of that too. So for I in range, so basically I'm going to check. Basically, if I'm trying to put a queen here, I'm going to check. If I'm trying to put a queen in this row, in this space, specifically in this row, I'm going to check these spaces. So I'm going to check this one, then this one, then this one, then this one, and so on for so forth to see if there's a queen. If board row and then column, not column, but I equal to 1, turn false. And we'll see that this still works. So now no queens are in the same row as one another. Another way I can do this is, and the way I prefer to do this, as you'll see why for the next, I'll do column minus I, which will start me checking here, and then check here. Then I have to increase by 1. Let's just keep it like this right now. We can burn that bridge when we get there. Okay, so now we need to do and is left is up left valid. Now, you might be thinking I need like a nested for loop or something to do this, but actually I don't, because I'm going when queens, they move at straight diagonals. So when I move up one space, the queen's also going to move up one space. Yeah, sorry, if I move up one row, I'm going to move up a column as well. The only thing is that, like, as you'll see, like to go up a row, I'll need to subtract 1 as opposed to adding 1. Adding 1 brings me a row down. So haven't written this one yet. So let's go ahead and do def. And believe it or not, this is the toughest part of this assignment of this assignment when I give it out, which is checking these issues. So for I in range, and let's go ahead and do this way, 0. And I want, so what I'm going to do is I'm going to give it a range, not to 8. Here's what I'm going to do. Rather than doing I as that amount, I need to start at row and column, and I need to radiate out from them. So if I'm going up a row, I'm going to subtract I, and then to go to the left, I'm going to plus. I'm going to start at the space I want to put a queen on, which will be blank. And then I'll start at the space I want to put the queen on, but up a row, and 1 to the left. Then 2 and up 2, and then up 3 rows and over 3 columns. Make sense so far? And I'm just kind of doing that in a kind of telling you what the answer is there, because, you know, it's 3 o'clock already. So now I actually have to figure out what number I'm going to put here, because I don't want to go, I want to make sure that this value doesn't become 0. Sorry, this value stays above 0. So, well, it couldn't be 4, because what if we're at the end? It's got to be, it's got to be a variable. So or it's got to vary. It's going to vary off of row and column. So let's go with so let's see, let's just type this out here. We want rho minus I to be greater than or equal to 0. Because once this gets below 0, once this gets into the negative range, that's technically out of bounds. So, okay, we need this to stay above we need this value to stay above 0. So the biggest so we don't want rho to be any bigger. So we don't want I to ever be bigger. So I must stay below rho plus 1. Once it gets to rho plus 1, game over, because that's out of bounds. Similarly, column plus I, that's going to go out of bounds if column plus I is greater than or equal to 8. 8 is an invalid column because the column values are 0 to 7 because there's 8 of them. So if column plus I goes above 8, then we're done. So I must be must stay below 8 minus no, 8 minus call plus 1. Or is that the case? Yeah, because if it was negative. All right. So what are we going to be here? Well, we don't want, so for I in range, we want it to be the minimum of, and this is actually where it would be easier in Java because the classical for loop is a bit easier in Java. In IBD, if I'm doing a classic for loop, it would look something like this. For int I is equal to 0. And actually, if I do this, I can translate this. I is equal to I plus plus, sorry, I plus plus over here because we're going up in our I. And our while condition is while rho minus I is greater than 8, sorry, is greater than or equal to 0. And then in other programming languages, the and isn't like this, and column plus I is less than 8. So instead of trying to force a square peg into a round hole, say, well, go ahead and split it up. While I is equal to 0. So I set I equal to 0. While rho minus I is greater than or equal to 0 and column plus I is less than 8, check that. Because if we check that, well, this is false, we could get, it could crash. And then we do I is equal to I plus 1 to increment it. Now, if we run it, let's go ahead and see if that's my most recent run. Did I call it? Is up left valid? Board row column. No, that did not work. So I well, rho minus I is greater than or equal to 0, and column minus I, column plus I is less than 8. If rho minus I, column plus I is equal to a queen, if we find a queen in my row column, which I should, and so when you get into an issue, yep, no. When you get into an issue like that, print rho minus I, column minus I, column plus I. And we see that we've got 0, 0. So from 1, 1. So up and to the left. So column increases. Oh, I have it reversed. Silly me. Not reversed, but the column, I forgot the column's going to the left. The column, I'd be checking this way, which is silly. And column, wrong dimension. So I was going right, I was checking to the right, not to the left. Silly me. And let's scroll down and look at that. We've got ourselves something that looks close to a solution. We still got a diagonal over here, but that can be solved by our last check, which is going to be and is down left. Valid. Board, row, column. Okay. And let's just copy this entire thing over here. So what we need to do over here is now that the row is going down, the row value, we're going low in lower rows, which means that the row value is increasing. Yeah. Row plus I is less than 8. And now we change this to row plus I. And so, and now we have 8 queens puzzle solved. Looks pretty good, I'd say. Now, what's interesting is when I was talking about Sudoku the other day, okay, and this is how I'm going to finish it up. I'm not going to be able to solve the entire Sudoku puzzle, right? Sudoku works in a different way, but the solve method is almost exactly the same. Def solve Sudoku. So for those of you who want to try it on your own, board, row, column. So here we're choosing to put a number at a specific row and column for Sudoku. For if you remember, what is Sudoku? Sudoku is a 9x9 grid, right? Sudoku is a 9x9 grid. And we want to put, and we need to put numbers such that each row, column, and 3x3 square has the numbers 1 through 9 in it exactly once. So what we do over here to do this is, what do I mean it's similar? Well, my base cases are a bit weirder, but that's okay. But you're going to see that basically the recursive part is almost exactly the same. So for this one, I say, hey, if the board, so first, if my row, it's a 9x9 board. So if my, so I'm going to go left to right across the columns. And if I'm done with a column, so if column is greater than or equal to 9, then I'm going to move on to the next row. Row is equal to row plus 1. And column is equal to 0. So go to the next row, start at the beginning of the row. And then if I do that and my row is now out of bounds, if row is greater than or equal to 9, well, if I'm out of rows to try, because I'm going across the rows, so I'm going to do the top row, then the next row, the next row. If I'm out of rows, then I'm done with the puzzle. Return true. Next, Sudoku comes with some places already some places already done. So if board row column is already fit, if that board position is already filled, and that position is already filled, not equal to 0, which I can just simply do by that. If there's something there, then I will just simply move on to the next one. Return solve Sudoku board row column, and then go on to the next row. Okay, so I'll just skip over it. Otherwise, I found where I am. Solving the entire puzzle is hard, so I'm just going to solve the single square. Okay, so I'm an empty square. I have 9 things I can put inside of this square, which is for num in range 1 up to, but not including 10. So 1 through 9. There's a bunch of things I can put in there. And then I ask myself, if is valid, which is going to be a different is valid function, but I would do board if is valid Sudoku. So then I'd say, hey, put a board row column. In that board row column combination, try to put that number in. If that works, then great. What am I going to do? If I can put, if it's a valid place to put that number, I'm going to put that number. And then I'll do my recursion, which says, hey, if solve, I'm going to try to solve the next space. Row column plus 1. Otherwise, clear the space that I was just working on because I got to a dead end. And look how similar this bit, the recursive bit, is to this recursive bit in Solve Sudoku. It's pretty much exactly the same. The difference here is that I'm using row and column. And so what changes between these things? These two things use the same exact strategy. The base cases change. And they have a different way of checking to see if it's a dead end. Stop share.